All right, welcome back to Easy Math with Nick. Today, early in the morning, we are on video number 16. And as promised, today's video is going to be on an AP Physics C FRQ. I chose to do this year's free response questions actually for today. So previously, I did a different recording of this video, which was that wind turbine problem. I think I might have mentioned in the last video, but I won't be uploading that one just yet because I think that video needs a little more refining. There's one thing I got slightly led slightly astray in that video for one part of the question, so I'll probably just have to edit that one. So that's why you see the one here today. So this question was on this year's exam, so I have seen it before as I took the exam this year. So it's not my first time looking at it, but it's my first time doing it since then. So the flashbacks are real with this one. So let's start. Two blocks, 1 and 2, slide toward each other on a horizontal surface. Block 1 has mass m, slides in the positive x direction with constant speed 2 v. Block 2 has mass 6m, wow, pretty heavy. Slides in the negative x direction with constant speed v0, v sub 0, as shown in figure 1. Blocks then collide and stick together. Ooh, that's why I titled this Inelastic Collisions, right? Important. The collision occurs from time t equals 0 to t equals t sub c. After the collision, where t is greater than t sub c, the blocks move together with the same constant speed. So they stuck together, now they're moving at the same speed. Okay, so let's see what part A asks us. The diagrams in figure 2 is down there by the way, can be used to represent, let's move this up a little bit because we don't need all this space. Can be used to represent the momentum blocks 1 and 2 before and after the collision. Momentum vector diagram for for block 1 before the collision is shown. They give it that here. That's nice. Draw arrows on the grid to represent the momentum vectors of block 2 before the collision and the 2-block system before and after the collision. Okay. The length of the arrow should be proportional to the relative magnitude of the vectors. Represent an arrow of 0 length by drawing a dot at 0. Okay, so there's no arrows of 0 length here. Pretty sure. So let's solve. Let's solve for the momentum of the 2-block system. The 2-block system after the collision. So we know that momentum is going to be conserved here because there's no external forces, right? These 2 blocks are sliding on a surface without friction. They're colliding and then sticking together. So there's no like external force acting on the system that would cause momentum to be not conserved. So if we're looking at conservation of momentum, we would have momentum block 1 equals the momentum of block 3. Sorry, the combined system. I should say P combined. There's no block 3, silly. So if we have the momentum block 1 is going to be mass times 2 VO plus, now because we're going in the because block 2 is going in the negative x direction, we need to account for the fact that its velocity is negative. Even though they give us the speed, they just give us speed, which is the magnitude. You need to take into account that the box going in the negative x direction. So equals P, I'll just say P comb. So when we work this out, we'll have 2m VO minus 6m VO, V sub O, whatever, equals P combined. So our when the blocks are combined, our final momentum is going to be negative 4m VO. And so this solves 2 of our unknown little things in figure 2 here, 2 unknown grids or squares in our rectangles in our grid here, because momentum is conserved. The momentum of the 2-block system before and after the collision is going to be the same. So what we draw in the 2 rectangles down here is going to be the same for both scenarios. So that's 1, 2, 3, 4. And down here, 1, 2, 3, 4. There you go. So I drew my 2 little arrows, and that would get you credit for those 2 rectangles. But now, what's the momentum of block 2 before the collision? Well, that was what, P2, right? And P2 was 6m. It was negative 6m VO. That was the momentum block 2 before the collision. And we are taking into account direction here as we draw these arrows, right? So momentum vectors, right? So we're taking into account direction because vector is magnitude and direction, right? So 6 MVO would be a little bit longer. So 1, 2, 3, 4, 5, 6, something like that, right? 1, 2, 3, 4, 5, 6. Yeah, something like that, right? And so you can see when we're adding these vectors, we get to this last step here, and that's how you know you did your work correctly. Because we had a vector length of 2 plus vector going the opposite direction of magnitude -6, so that gets us a vector in that left direction, magnitude -4. That makes sense, right? It's all in the same horizontal plane. So, okay, that was a pretty light question to start off with, but let's move on to part II. During the time interval between 0 and t sub c, which we said is when the collision ends, right? A force F is exerted on block 2 by block 1. That's important. Along the x direction, as a function of t that is modeled by f of t equals f max sine a of t, where a is a positive constant and f max is the magnitude of the maximum force exerted on block 2 by block 1 during the collision. Derive an expression for f max. Express your answer in terms of m, VO, a, and t sub c, physical constants, as appropriate. So the reason they say it's important to see what they want you to put your answer in terms of here, because we can't just divide both sides by sine of at to get f max, right? That doesn't really work here. We need to work with what we have. What type of question is this? A momentum question, right? So they're not just throwing this at us to confuse the hell out of us. They're throwing this at us to see if we know the relationship between force and momentum. So if you want to start out with the equation from the reference sheet, I'm pretty sure this is on the reference sheet. Doing part II, I'll do it up here. F of t equals the derivative of momentum with respect to time. So, or if you, because the reason this is true is because F force equals ma. So that's why that's true if you're wondering. And dv/dt is acceleration. So force equals mass times acceleration. We know that, right? So this is going to help us solve because we know momentum from the last question. And we're dealing in the same scenario here. It's not new scenario as part B seems to be. This is the same scenario. So if we multiply both sides by dt, we'll get dp. Oops. Need tissue. F of t. dt. And now let's substitute f of t, dp, the mass, the momentum differential there on the left. And on the right, we have f max, which is what we're solving for. Sine a of t, where a is a positive constant, they said. So at dt. So now, in order to work with the momentum that we had before, we need to, in order to work with what we had in part A, we now need to integrate both sides with respect to time and what we're going to get, what our limits are going to be. My bad. We're going from t equals 0 to t equals tc. Even though I don't think I need to put the limits on both sides like this, it's good to show. Now it's good to show that because that is the time interval they're giving us, right? So if we continue to, if we look on the right now, that's going to get us delta p. We're going to get delta p on the left. Sorry, on the left. But what is delta p? We're looking at what? On block 2 by block 1. So we're looking at the change in momentum of block 2. So this is the change in momentum of block 2. Well, what is the change in momentum of block 2? Well, block 2's initial momentum. We were just looking at block 2. Block 2's initial momentum was what? This. We found this, right? -6 MV. This was block 2's initial momentum. But what is its final momentum? Well, it is not this here. You might think it's this number here because that's the final momentum of both blocks when they're combined, but that's not. That is both blocks, right? We need to take into account just block 2 here. So it's just going to be, what's that final speed there after the collision? final speed after the collision was. Give me a second here. Yes, I don't think they even asked for that, but you need that to solve this. So we'll have give me a second. Move together with the same constant speed. Okay. Did we even solve that? No, I don't think we did. Okay, no, let's do that now. Okay, I was thinking we might have solved for that before. So we'll have what? Negative 4 mVo equals, we're dealing with 7m because we're dealing with the combined mass, right? It's m plus 6m, v final, whatever that v final is going to be. And this is also, well, okay, this is also in that direction. What for direction? Give me a second here. Yes, this is also going to be in the left direction. So I think the negative signs will cancel out. But actually, no. Leave it as is. So we'll have negative 4 over 7 VO equals VF. So that's our final velocity. The reason why I do this is because now we need to multiply that final velocity by the mass of block 2 to get the final momentum block 2. So the final momentum block 2 is going to be negative 24 over 7m VO P2 final. The reason why I do this is because now we could find delta P2. But before we continue, let's hold our horses here because we still need to integrate the right side. So if we pull out the constant F max, which is what we're solving for, don't forget that. I'll just write 0 to TC now. I don't need to be fancy. We'll have sine of AT dt. And this is the format of an integral that's on your equation sheet. So if you don't know the integral of sine, too bad. What can I say? It's negative cosine. But, and also you need to account for that. You're pulling out the account for the a within the sine function. So that's going to be negative 1 over a cosine of a of t. So delta P2, let's substitute in delta P2 now. So delta P2, which is the change in momentum on block 2, is going to be the final momentum block 2 minus the initial. So 24 over 7 mVo minus the initial. The initial was negative, so minus a negative. Subtracting a negative is going to get you a positive. 6 could be written as 42 over 7 mVo. This is the 6 mVo we had, which was the initial. So that's why I'm rewriting it as 42 over 7 to make our work easier. So I don't have to pull out a calculator. I might do this all without a calculator. Wouldn't that be something? But use a calculator if you could. I used one on the exam. I'm not trying to be like funny. Don't be that guy that tries to do the whole exam without a calculator and then fails it. So that would not be very fun. Let me erase instead of undoing all that. I want to use brackets here to, when we evaluate the limits. Cosine AT. So if we took the derivative of this, we would get 1 over a sine of a of t times a, which would get rid of the constant out front because a over a is 1. So that would get us back to sine of a t. So that is correct. That is a correct antiderivative. And we're going to evaluate that from t to 0. Okay, now if we look at, let me move this down a little bit. Those lines aren't going to make sense anymore, but whatever. I'll get rid of them. Turn this down a little bit more. There you go. Oof. Now we can, let's simplify both sides. So negative 24 plus 42, that is what? 18 over 7. Is that correct? That sure does look correct to me. Mental math. Woohoo. And on the left here, to evaluate what we have there, the bottom limit does matter because when we have a 0 with cosine, that doesn't mean we just ignore it. We're going to have negative 1 over a cosine a of tc minus, well, plus 1 over a Because when we plug in 0 to that expression, we're going to get what? We're going to get negative 1 over a cosine of a times 0. A times 0 is 0. Cosine of 0, 1. 1 times negative 1 over a, negative 1 over a. Subtract. When we're subtracting negative 1 over a, we're subtracting a negative, which gets us a positive. So there you go. Can we simplify this more? You bet your bottom dollar we could, but we don't need to. Actually, I will. I'm going to pull out a 1 over a. You don't need to simplify on the exam, but it can make it easier to check your work. And now in the parentheses, we're going to have 1 minus. I just flipped the terms around, by the way. That's what I did there to be fancy. And now we can solve for our answer. So we're going to have 18 VO times A over 7, 1 minus cosine A T sub C equals F max. Oh boy, isn't that a fun answer, right? That is one of the answers of all time, but that is something. Okay, let me make sure that looks right. Okay, I don't quite know the units of A, but it's positive constant. Okay, what's the correct unit? I guess it might be unitless. Okay, I think we're in the right units here. No, I think this is correct. This looks right to me. I evaluated that expression correctly. I evaluated the integral, correctly. I think I found the final initial momentum of block 2 correctly. So I think we did that right. Yeah, and then we multiply by 6m to get negative 24 over 7. Negative 24 over 7 plus 42 over 7, because that's what, 6. That's what we had. Subtracting a negative. Okay. I think that's right. That was a very that was longer than I remember it being. I remember this being an easier question, but yeah, that is the work for that one. So yep, I think that's right. The answer is very unwieldy. I remember it being that unwieldy, but the units there, I know the MVO gets units of momentum, but when you divide by sine of AT, does that, I'm sorry, when you divide by the 1 minus cosine of A of t, I mean, I guess A has to have a unit, right? I guess A has to have units. Okay. Okay, that's a little bit weird. I don't know what to think about that. Okay, whatever. I did the unit check is hard there because you don't know the units of A, but I think everything else we did correctly, so I'm not going to sweat that so much. Okay. Okay. Yep. I think we're good there. Okay, let's move on. Okay. Consider a new scenario where block 1 initially slides in the positive x direction with a new constant speed v1, and block 2 initially slides in the negative x direction with constant speed v sub 0. Blocks require to stick together. In the new scenario, the two-block system has constant speed VO after the collision. So we don't know the relative magnitudes of V1 and VO, but if the two blocks are going to have speed VO after the collision, so we're starting out with a scenario like this, where this is block 1. It's going in positive x direction with speed v1, and block 2 going negative x direction with speed v sub 0. If they come out of, if they now stick together, and finish with speed v sub 0, it's hard to see that the scenario at which without knowing the relative magnitude, it's hard to say this for sure, but it's hard to say that v sub 0 is going to be much greater than v. I think v1 has to be greater than v0 in terms of magnitude. because V0 would have to be so great that it overcomes V1. And then, but it could be, though. That's the problem. You don't necessarily know that. Um, Okay, yeah. I guess it could really go either way, but we're gonna go with the assumption that V1 is greater than V0 because I don't see it. I don't see V0 being so great that the blocks are now going to start moving in that other direction. And remember, block two. Okay, no, block two was the one with more mass, right? So, okay, if block two has more mass, okay, that changes things. That changes things. We're going to have M V1 when we look at our total momentum minus 6M VO equals 7M. We're solving for this VF, right? What is VF? If V1 is greater than VO, V1 would have to be much greater than VO in order for our final velocity to be positive. So, okay. But it could be. That's why what I'm trying to do here is I'm trying to find the direction of the blocks after they collide, which I just don't think we know. So I'm just going to work here with I'm just going to work here with the assumption that V1 is just much greater than VO, because I remember doing that on the exam. So, and not thinking too much about it like I am now. Derive an expression for V1 in terms of VO. That's what we're going to do here. So, fundamental physics principle, P1 plus P2 equals P final. Conservation momentum. Momentum still conserved here, so that's what that is on this part B. It's the same. It's the same scenario as before, except we're changing the speeds, which doesn't change the fact that there's no external forces, right? So I'll do what I was doing on the side there, mv1 minus 6mvo, 7mvf. Okay, whoa. I'm sorry, VF, they told you, okay. And they have speed V0 after the collision, my bad. They tell you that, oops. I was like, wait a second, yeah, that's a little confusing, right? They have speed V0 after the collision. But do we know the direction of that? Not necessarily, but we're trying to just find speed, right? V1 is small speed, right? So I don't think maybe direction doesn't matter here. Who knows? But we'll have mv1 equals 13. V1 equals 13 VO. And that is your answer for part B. So I think that's correct. I think we just neglect, when we're working with speed here, I don't think we need to stress too much about what the sign on V sub 0 is going to be on the right there. I was stressing about that, but I don't think you really need to. Because that's what, in a way, we're solving for, kind of, right? And we're just dealing with speeds here. So, yes, you do need to account for the negative sign here, because it's not like both blocks are moving in the same direction. You can't just neglect the fact that they're moving in opposite directions before they collide. But I think 13VO was your answer there. That's a little bit of a tricky one when you really think about it. If you don't really think about it too much, you just get your answer that I got and you're fine. So this question wasn't so bad, in my opinion anyway. For the first question on the exam, this one wasn't that bad. The first part, part I, was a joke, complete joke. In my opinion, if you think otherwise, I'm sorry, but it's just drawing arrows. That is not very difficult. That one wasn't so bad. It is a very good question to test your knowledge about momentum, about conservation of momentum, and about how the momentum of the two-block system before and after the collision looks the same because momentum is conserved. So as long as you're familiar with the idea of conservation of momentum, part A isn't that bad. Part AI isn't that bad. II, on the other hand, that one's a little bit difficult. This one utilized calculus and is the most calculus-heavy part of the exam, in my opinion. When I took it, this was the most heavy question. The sine integral was one of the more difficult integrals on the exam, I think. Nah, I don't even think that's true, but whatever. It wasn't. It did get a little complicated here. Just looking at this, there might be a mistake somewhere in there, but I doubt it. I think that is the correct answer. It just depends on what the units of A are. if the units are I'm assuming that the units of A could be 1 over time. I'm sorry, like 1 over seconds, which would make my answer correct in the correct units. So hopefully that's true. If it's not, womp womp, but whatever. I think the units do check out there. I think everything else we did right. We are looking at block 2. That's important. The force exerted on F on block 2 by block 1. That's what I had underlined before. That is very important. Exerted on block 2 by block 1. So when we look at when we integrate the momentum differential, we're going to get the change of momentum of what? Of block 2, not block 1. We don't care about block 1. Block 1 is just what is causing the force, right? So we don't care about its change momentum. We care about the change momentum block 2. And so the change momentum of block 2, we know it's initial momentum, right? We knew that in the last problem. It was just 6m negative 6m v up. That's fine. But we need to know its final momentum, which is not the same as the momentum of the system. Even though the blocks do combine, each block still has its own respective momentum. It's just the block itself. So in order to find that, you need to first find the final speed of the system, or the final velocity of the system after the collision, which I thought we did in part A, but they didn't actually ask you to in part A. But now you can do it part C by as we did there, and we get negative 24 over 7 MVA. The final velocity, we take into account that the final velocity is negative. We don't need to include another negative sign because that would be redundant. I think that's what I was fussing over about before too. Oops. That is how we found the final momentum block 2 to be negative 4 over 7 VO, because that is what the speed of the two blocks are going to be. And we multiply that by 6m, the mass of block 2, to get negative 24 over 7 MVO. And now, when we bring that down there, we'll have final minus initial momentum, because that's what delta symbolizes. So final is going to be negative 24 over 7 minus 6 minus negative 6, so that's plus 6, which is 42 over 7. Remember your times tables from middle school, right? I think, yes. Okay. I'm sorry. I'm not fussing over the 42 over 7. I was just looking on the right side. Okay. Yeah, our limits were right. So, I think we did everything in this question correctly. I'm not gonna sweat it too much. I think the answer is a little bit unwieldy, but besides that, that's all for today. This was a free response question number 1 on this year's exam. I'm aware that some students had different versions of this year's exam, regardless as if you took it as a retake or not. So you might have not seen the same question if you took the exam this year, but I did. So this one was sort of familiar to me, but not too familiar because the exam was a couple months ago at this point. So thank you for watching. The next video should be on statistics. So looking forward to that one. See you then. Bye.